Let me show you what happens when we don't follow this principle. When modules expose their internal representations, every client becomes coupled to those implementation details. This creates what I call the coupling cascade. Consider this example of transparent data. We have a book class where everything is public. The title is a string, the author is a string, and the publication year is an integer. Now, this might seem convenient at first, but it's actually a coupling disaster waiting to happen. Now, here's what clients inevitably do with this exposed data. They sort books by comparing author strings directly. They create display text by manipulating the title string. They determine if the book is old by comparing the integer year to some threshold. They create JSON by depending on the exact field structure. Every one of these operations couples the client code to the internal representation. Now imagine you need to support internationalization, where names need multiple language, or complex date with different calendar systems and BCE dates, or rich metadata like ISBNs, editions, and publishers. Every single client needs to change. Your simple refactor becomes a project wide migration. This is the maintenance nightmare that representational independence prevents. Let me paint a picture of how bad this can get. In one code base I worked with, a simple change to support multiple currencies in the system required editing over 200 files across 15 different modules. The change took 3 months and introduced countless bugs because every piece of code that touched money had to be updated. This is what happens when you don't hide your representations. Now let's talk about the solution. I want to give you the formal definition because it's important to understand this precisely. Two representations are observationally equivalent if every public operation yields the same observable result on both. A client that cannot distinguish one representation from another is independent of the representation. This means that if I have two different ways of storing the same information internally, and clients can't tell the difference through any operation they can perform, then I have achieved representational independence. There are three key ingredients to making this work. First, you need private state. Representation variables are not visible outside the module. Second, you need an abstraction function that maps concrete state to the mathematical value it represents. And third, you need an representation invariant, which are conditions that must hold for every reachable state. When all public methods preserve the representational invariant and honor the abstraction functions, clients interact with the abstraction value alone, never the concrete representation. This is a profound shift in thinking. Instead of exposing data, you expose behavior. Instead of letting clients manipulate your internals, you give them operations that accomplish their goals while keeping your implementation flexible. The mechanism we use to achieve representational independence is called an opaque data type. An opaque data type lets client hold values of that type and exposes operations that manipulate them, but hides the structure that makes those operations possible. Think of it like driving a car. You can operate the car through its interface, the steering wheel, pedals, the gear shift, without knowing how the gearbox works internally. The gearbox representation is opaque to you as a driver. Different programming languages provide different mechanisms for creating opacity. In Java, you use private fields, package private fields, and interfaces with factories. In TypeScript, you use closures, private members, and branded types. Go provides unexported struct fields. Rust has module visibility and the new type pattern. C++ offers private members and the p-imple idiom. The key insight is that regardless of the language mechanism, the goal is the same: make it impossible for clients to depend on the internal structure. Now, let me walk you through a detailed case study that shows how a book class can evolve from a transparent disaster to opaque excellence. This will illustrate the principles in action. In version 1, we have transparent data. Everything is public for convenience, but this creates dangerous dependencies. The title, author, and publication year are all exposed as their raw types. Now, clients would typically immediately couple to this raw representation. They create sort keys by calling two lowercase on the author string. They build HTML by concatenating the title string. They determine if the book is classic by comparing the integer year. The problems with this approach become apparent quickly. You cannot support multiple languages. You cannot handle complex dates like BC years or different calendars. You cannot add metadata without breaking serialization. You cannot optimize internal storage. Every client becomes a maintenance burden. Now, version 2 shows what I call half measures. The fields become private and we get add getters, but we are still in trouble. The getters expose the representation just as effectively as public fields did. Clients still couple to the representation through these getters. They still depend on the author being a string and the year being an int. The representation is still leaked, just through a different mechanism. Now, this is a common mistake. Adding getters and setters doesn't automatically give you representational independence. You need to think more carefully about what happens, what operations clients actually need. Version 3 shows full opacity with domain types. Now we use localized string for the title and author, and publication date for the publication date. The constructor take domain types, not primitive types. The behavior interface is stable across internal changes. We have a citation method that takes a locale. We have a published before method that takes a year and calendar system. We have a we have an is contemporary method that compares two books. We have a compare by author method that handles localization properly. Notice how each of these methods expresses client intent rather than exposing structure. Clients don't need to know that titles are stored as localized strings or that dates use complex calendar logic. They just call methods that accomplish their goals. Now, the supporting domain types are also opaque. Localized string hides a map of translations and provides methods to resolve text from different locales. Publication date hides complex date logic and provides methods for comparison and for display. Look at how clients use this opaque interface. They sort books using the compare by author method. They create display text using the citation method. They check age using the published before method. Notice that none of these operations depends on the internal representation. The benefits we achieve are substantial. Internationalization is hidden behind localized string. Complex dates are hidden behind publication date. Future extensions like ISBN, publisher, and edition can be added without breaking clients. Performance optimizations like caching and compression can be implemented internally. The entire internal representation can evolve freely. This is the power of representational independence. The interface remains stable while the implementation can change dramatically.